Okay, in the previous lab, we've considered a slotted waveguide antenna. So this is essentially an antenna array for us. So we studied this, and now in this lab, we're gonna be focusing on a different antenna array, which is a microstrip antenna array, which is based on exercise 3-3 of LabVault student manual. Now, before showing you the microstrip antenna array that we're going to be using, I'm going to show you the microstrip antenna or patch antenna that we used in a different lab. So this is a single antenna element. Now, in this lab, we're going to be using an array of microstrip antenna. So the first one that we will be considering would be parallel fed microstrip antenna array. So if you look at this structure, you see a parallel fed microstrip antenna array. So in this case, essentially we're using transmission lines to feed different elements. Now, if you look at this structure, this essentially consists of three main parts, the feeding network. This is a parallel feed, or you may also call it corporate feed. So this is essentially consists of three main parts. So if I write it here, so the first one is parallel feed or corporate feed. So of course you have your transmission line. So this is, for example, your 50 ohm microstrip transmission line that you start the feeding network with that. Then you sometimes you need to go to a different transmission line. For example, let's make an example that you want to go to 250 ohm from both sides. So 50 ohm here and 50 ohm here. So that would be very similar to this structure where you start with a 50 ohm and then you go to add two other 50 ohms here. So of course, when you do something like that, you essentially need to divide the power. So there is a element which is power divider here, but you also need to be careful because now if this is 50 ohm from this side, this is 50 ohm from this side, then it looks like 25 ohm from this side. So here you need to have a quarter wavelength transformer with the characteristic impedance of 25 times 50. So the square root of 25 by 50, and that's going to give you a quarter wavelength transformer. So that would be your quarter wavelength transformer here. I'm plotting that wider than the 50 ohm because, as you know, the smaller your characteristic impedance, the wider it becomes. So then this is going to be your quarter wavelength transformer and essentially power divider too. So you have transmission line, you have a junction with quarter wavelength transformer. So you immediately see two components of it. The other component is that when you are using this type of feed network, you're gonna have bends sometimes because you go to a different direction. So you're gonna have for example, 90-degree bends, for example. So imagine if you want to have 90-degree bends, for example, you might have a transmission line like this. And now all of a sudden you need to bend 90 degrees. So this would be your bend, essentially. But if you do it like that, then there could be some problem with the characteristic impedance because of this bend. So one way to handle this is essentially to miter this transmission line and have it in this form. So now how much you need to do that, these are all also design parameters and there are formulas for that. But essentially this shows a structure that you are using this type of bend to change the direction of your transmission line by 90 degrees. So these are essentially the three main components of this parallel FET that we have. We have our transmission line, we have our power divider with quarter wavelength transformer. We have our bend, and now of course these are gonna go to our patch antennas, and they're gonna be feeding our patch antenna. So that's the introduction to this parallel FET that we have. And then the next one that we're gonna consider would be the series FET patch array. So in this case, you have 4 patch, and then you have a 50 ohm that's tapered to a different transmission line here, and that would be the other antenna that we are using. So in the lab, we're going to look at the half power beam widths of these antennas in the E plane and H plane. We're going to also, at the end, we're going to use a standard gain to calculate the gain. There are a couple of more experiments in the student manual that uses copper tape, and those are not included in this video lab that I'm recording. So we're going to get to the half power beam widths and the gain of these. And when you are looking at these patterns, always have the idea of the size of the antenna in each of the plane in mind to be able to justify the results that we get. And also remember that there is one thing that's not included in the equation that we learned in the class for the array factor, and that's the mutual coupling between the elements. So when you have mutual couplings between the elements, that's essentially not included in that equation. So they could potentially create some discrepancies for us when we are looking at our results. So we're going to investigate them more. Okay, in this lab, we're going to be testing this parallel fed microstrip antenna array. I mean, as you know, the other name of this type of feed network is corporate feed. So one thing that's important for our measurements here is that to note that the electric field of these patch antennas due to fringing effects are all vertically polarized. So the electric field is vertically polarized, and then the direction of main beam is broadside, so it's toward you. So if that's the direction of electric field and then the direction of maximum radiation, this is essentially my E plane. So that's my E plane, and therefore this would be my H plane. So this is my H plane again, so if I start rotating the antenna like that, I'm measuring the H plane cut of this antenna. So that would be my H plane that I'm gonna measure right now. So again, that's the electric field, and I'm measuring like this. So I'm measuring H plane. But since our purpose here is to measure copole, so we need to make sure that the transmitting antenna is also have the same polarization as this. So this is the electric field is like that. So you need to have a transmit antenna which is also vertically polarized, and our transmit antenna is our horn antenna. So essentially, again, we have a horn antenna which is vertically polarized, which is matched with this, and then we're rotating like that, and that would be our copole H plane. Something to keep in mind is that this is the center of this antenna, and that should be aligned with the axis of rotation. So if this is the antenna mounted here, so this line here should be aligned with the axis of rotation. So we're gonna have a closer look at this antenna, and then we're gonna start our measurement. Okay, we have our microstrip antenna array with parallel feed or corporate feed mounted. One thing to note here is that the center line of the antenna, which is this line over here, that should be aligned with the axis of rotation. So if I get the axis of rotation here, if you start from here and go up, that's your axis of rotation. So this is the part this is the axis over which we are rotating. So that's our axis of rotation. So, and then of course the antenna right now is mounted in the H plane. Remember that the electric field of this antenna is now vertically polarized. So the polarization is vertical polarization, and that's why if I if I move to the other side, you can also see the horn antenna that act as the transmitter, and this is also vertically polarized. So I have vertical polarization to vertical polarization, and the antenna moves in its H-plane. So essentially that would be copole H-plane. So I'm going to have a closer look at the antenna so that you can see it better. So we have 4 elements on one side, 4 elements on the other side. We have our transmission line, we have our power splitter, we have our quarter wavelengths transformer. So the other thing to note here is that according to LabVolt manual, we have separated the patch antenna, this patch array, from the horn antenna by 1.6 meter. So let's start our measurement to find the H-plane pattern of this antenna.
Okay, we have now our microstrip antenna array with parallel feed or corporate feed mounted. Currently, it is in H-plane configuration data collection. And it's also matched with the polarization of the transmit antenna, so we will be collecting copole H-plane. I already applied 18 dB of attenuation in the software, as you see on the right column, and now I'm gonna start my data acquisition. As I mentioned in the previous video, the distance between transmit and receive antenna is at 1.6 meter as the instruction of the LabVolt student manual. So let's start our data collection. As you see, we don't get anything. The reason is I forgot to start the RF power. So I'm just gonna start the RF power and we go back to the measurement. So I'm gonna stop the measurement and go start the power. Okay, probably you hear this beep. That means the RF power is on. Now we're gonna start our measurements. So right now we are approaching the back lobe of this antenna array. So this is our back lobe. Now we are approaching to the side of the antenna, and of course after completing the side, we're gonna go to our main beam. So this is gonna be our main beam now. And now the data collection is done. So we're gonna be saving this under H plane of parallel fed patch. So this is now saved, and to be consistent with everything we've done, we set the maximum signal level to be 0, so to have this type of radiation pattern. So if we look at it right now, the maximum signal level, if you read from the right column, is minus 3.16 dB, and half power beamwidth that we got is 15.94, approximately 16 degrees. So that's our H plane. Now, of course, the next step is to go for our E plane.
Okay, so right now the antenna mounted like this. As you remember, this was H-plane, so when you rotate like that, you collected the H-plane cut. But now remember that E-plane from our previous discussion is this plane. Now, using this system, you cannot rotate your antenna in this plane. So the trick that we always did in this course is that to perform measurements in this plane, which in this case is E-plane, we rotated everything 90 degree. Now, if I rotate my antenna under test 90 degree and I rotate it like that, which is supported by the system, now I have my E-plane cut. So instead of mounting antenna like this, you rotate it 90 degree. Now all of a sudden you're measuring E-plane cut. And remember, because you rotated your antenna under test by 90 degree, you also need to rotate your horn antenna by 90 degree to have polarization match. Right now, horn antenna is providing vertical polarization, but if you rotate your antenna under test by 90, that's the direction of electric field, so it expects horizontal polarization for copole E-plane. So in this case, you need to rotate the antenna under test by 90 and also your transmit antenna, which is horn antenna, by 90 degrees, and then you can collect E-plane. So let's go and do that and then start our pattern measurements. Okay, as you see, we've rotated the antenna under test 90 degree compared to the previous case. So based on this configuration, we will be measuring E-plane cut. So I'm going to have a closer look at the antenna so that you can see it better. So if you remember, the feed was coming from bottom to the antenna. This time is from the side. That's an indication of the 90-degree rotation. You can compare it with previous videos to see. So that's our E-plane. But as soon as we've rotated it right now, now the polarization is horizontal. So to handle that, we need to be able to provide horizontal polarization for this antenna to get the copole E-plane. To do that, if you look at the horn antenna that we have here, we've also rotated our horn antenna 90 degree. So if you look at the waveguide adapter, you can realize that this is in fact a horizontal polarization. So now this is horizontal polarization. The other one, which I mean the receive antenna, is also expecting horizontal polarization. So I'm going to be collecting E-plane cut using this setup, copole E-plane cut. So let's go and see what would be the radiation pattern of this patch antenna. Just before maybe starting seeing the software, let me just press the data collection button, and then you can see a little bit of movement of the antenna. You've seen that several times, but let's briefly also uh, check that. So I've just started the RF generator, and now I'm gonna go and press the data acquisition button so that the transmit antenna start rotate. So as you see, it actually goes to the back, so it's going toward the back lobe collection. So that's my back lobe right now. Later on, you can see that in the software. So also you can keep an eye on the axis of rotation, and the axis of rotation, I tried my best to align the antenna with the axis of rotation. Now we are going to the main lobe of the antenna, of course, and now our data collection is going to be complete. So let's go and see what sort of a pattern we got in the LabVault software.
Okay, we have now mounted our antenna, which is a microstrip antenna array with parallel feed or corporate feed in the E-plane data acquisition mode. The polarization of the transmit antenna has been adjusted to be horizontally polarized to match the antenna under test. So we're gonna start performing our measurements. So let's start the measurements. So right now we are antenna look from its side to the transmitting antenna. Now we are little by little approaching the back of the antenna. So right now we are almost at the back. So and then gradually we're going to the other side of the antenna. So antenna looking from its side. So now still we are at side. Now we are approaching to form our main beam. So it is done. I'm gonna store it under our E plane. So this is essentially under our E plane. So we have so let's see if we want to be consistent with previous H plane, I need to rotate the maximum signal level to be at 0. So I just did that, and this is my pattern. So if you look at, this is my E plane, this is my H plane. So again, E plane, H plane. Now, one thing that you know is that we should expect a similar signal at the maximum for these two antennas. So the H plane was minus 3.16. The E plane is minus 4.19 for the maximum signal level. If you look at the right column, you see minus 4.19 for E plane, minus 3.16 for H plane. So that 1 dB we accept it to be okay uh, for the sake of this experiment. Now, if you look at half hour beamwidth of H plane, is it 15.94 degrees? For E plane, it is 34.89 degrees. So the first thing is that the half hour beamwidth of H plane is narrower than the half hour beamwidth of the E plane. So that's a question for you, why that's the case. Why do you expect a narrower half hour beamwidth for the H plane? Now, the second question that I have for you is that if you look at H plane is I mean very nicely almost symmetrical, but when it comes to E plane, you don't have that symmetry around the main beam. For example, if you look at this side lobe and this side lobe, they're completely different. Now, can you justify this? Does that make sense? So that would be another question for you to explain why, what's the reason for this, if that makes sense, or what's I mean, if it doesn't make sense to you, also state your reason.
Okay, we have now completed our discussion on the parallel fed or corporate feed patch array, and now we go to series fed patch array. So as you see here, we start with the transmission line, and this transmission line is tapered to go a different transmission line with a different characteristic impedance, and then you first feed the first patch, then in series you go to the next patch, and so on. So the signal is coupled serially between the patches. So if you look at this structure, you see that the amount of transmission lines that you have uh, is less compared to parallel fed. And this is an advantage in terms of loss, especially when you go to higher frequency, for example, in the millimeter frequency range. That could be an advantage for you. On the other hand, as you see, the physical lengths of the transmission line connecting these patches are fixed. So the physical length is fixed, but the electric lengths will vary if you change the frequency. So if you change the frequency, then the phase that you are providing to different patches could be different. And so if you know that if you change the phase, you can steer the beam. So that could be an issue for this type of feeding, that you need to be aware of that. And uh, you need to think about that in case you need some bandwidth. So currently this one is going to have a narrow bandwidth, the feeding network, I mean. So now we're gonna focus on the E plane and H plane data acquisition. So similar to parallel fed, let me remind you that the fringing field over the patch is in this direction right now. The direction of maximum radiation is toward you. So in fact, this is my E plane. So that's my E plane, and this would be my H plane. So if I want to perform H plane measurement, I can easily rotate like that, and I'm going to be measuring in the H plane, of course. So that's my H plane. But when you do that, be careful that the polarization of the antenna in this orientation is vertically polarized. So you want to make sure that your horn antenna is also vertically polarized when you do this measurement. Now, if I go to E plane, which is this plane, I cannot rotate my antenna in this plane. So what I'm going to do is I'm going to do a trick. I'm going to rotate it 90 degree like that. Now, if I rotate it, it's going to be E-plane. But remember, when you do that, now the polarization is horizontal. So you want to rotate your horn antenna also 90 degree so that you can measure copole E-plane. So we're going to first do an H-plane data acquisition, and then we're going to do E-plane data acquisition, and then we're going to compare them together. Okay, in this video right now, you see that we have our horn antenna vertically polarized. That's our transmit antenna. And now we're going to go to our antenna under test, which is series fed patch, which also expect a vertical polarization. So it has been mounted right now. I'll get closer to the antenna so that you can see that more clearly. That's our series fed antenna right now. So now I'm gonna start data collection, and as I explained, this is with this type of rotation, we're gonna get H plane because the polarization is also matched. That's gonna be our copole H plane.
Okay, right now on the screen we have H plane and E plane of our parallel fed patch array. Now we're gonna do another measurement this time. I can, for example, let's say hide these two that we have so that we have a empty screen. Right now we have our series fed patch array, and this series fed patch array has been mounted on the mast such that we are collecting H plane. So I'm just gonna start H plane right now, uh, and then we're gonna go to E plane and then compare it. So to do that, let me start the RF signal. Okay, the RF signal is now on. I have polarization of the horn antenna vertically polarized. Polarization of the antenna under test is also vertically polarized, and I'm rotating it in its H plane. So let's start our measurement and see what we're gonna get. And I kept the same distance as in the previous case as instructed by the lab vault student manual. So as you see, we have some ripples that ideally we want to investigate and see if we can reduce the ripples. So we are getting to the maximum signal level of the antenna, and the measurement is almost done. So I perhaps need to do more work on the measurements to make it cleaner. It has some ripples right now, but I'm just gonna accept it as it is for now. So let's store it under H plane and press OK. And also to be consistent, let's let's rotate the maximum signal level to 0 degrees. So this is the pattern that we get. Now for comparison purposes, it's also good if I bring the H plane of the parallel fed. So you see that it was much more directive compared to this H plane. And the other observation that you might have here is that you see that the maximum signal level has also been dropped between these two antennas by about 1 point maybe 5 dB almost. So here so I think it's more than 1.5 dB. The maximum signal level right now, it's minus 3.16 for the H plane of this, of the parallel fed. For this one is minus 5.67. So for series fed, minus 5.67. So we have about 2.5 dB signal drop between these two antenna. So that's something that we should keep in mind when we are comparing the gain of these two antenna. Of course, these are measured gain. I might have made mistakes in the alignment, in the distances, and things like that. So let's go and mount the antenna in the E-plane and perform the same data collection.
Okay, we have just completed performing H-plane of series fed patch array. Now I've rotated the series fed patch array by 90 degree and mounted it on the receive mast. So you see the structure that has been mounted. So now if it rotates using this configuration, this is essentially E-plane. Just one thing to keep in mind here is that if you look at this patch array closely, you see that the polarization that this needs to receive is horizontal polarization. Look at the feed line, and then you can figure out that it expects horizontal polarization. Therefore, our horn antenna subsequently needs to be rotated by 90 degree. I have done that already. So now if you look at the horn antenna, especially if you pay attention to the waveguide adapter, you can see that this is also now horizontal polarization. So we can now, everything is ready. We can start performing our copole E-plane cut measurement. So let's start that, and I'm just going to show you the collected pattern in the lab vault software.
Okay, on the screen you see the H-plane of the series fed patch array. So this was our H-plane of series fed. This was the H-plane of parallel fed. So I'm just gonna uh, hide the H-plane of parallel fed. It's just the H-plane of series fed right now. In this measurement, we're gonna go to the E-plane of the series fed. So let's start our measurement to see what would be our pattern. So right now we are looking from the side of the antenna, and here essentially we are at the back of the antenna. So back lobe would be here, and again we're slightly now gradually going to the other side of the antenna in its E-plane. So now we are gradually approaching the main lobe of the antenna. So this is our main lobe. Okay, that's essentially the pattern that we have. I'm gonna store it under E-plane, and this is my E-plane right now. So if I want to be consistent, I need to have the maximum signal level at 0 degrees, and this is essentially what I have. Now, Now, a couple of things to note here is that the maximum signal level of E-plane and H-plane match almost perfectly. The E-plane has a maximum signal level of minus 5.57. The H-plane has a maximum signal level of minus 5.67. So they're essentially the same thing with only 0.1 difference. And if you look at the half power beam widths, in the E-plane, we are having a smaller half power beam width of 19.24 degrees, and in the H-plane, we have the half power beam width of 71.53 degrees. Now, I'd like to justify that why, in this case, the half power beam width of E-plane is smaller compared to that of H-plane. The other thing that you notice here is that these two lobes in the E-planes are not symmetric. Can you justify that? and see if what could be a possible reason for that, or if you think that's a measurement error, you can also indicate that. So these are, and remember, these two things were when we are almost at 90 degrees, so we are looking from side toward the transmitting antenna. So yeah, that's essentially our E plane and H plane. I can bring the E plane and H plane of the other antenna, which was the parallel FET here too, so that you can have everything on one plot. So this is the H plane of the parallel FET. This one here is the H plane of parallel FET. This was the H plane of series FET. On the other hand, this was the E plane of parallel FET, but then this was the E plane of series FET. So you can compare these and answer the questions that was asked and also asked in the student manual of Lab Vault.
Okay, now that we have measured the E plane and H plane of series fed patch array and parallel fed patch array, and we have the maximum signal level of these two antennas, it's good to also calculate their gain, because right now we only have maximum signal level, which depends on different situation. For example, what is the distance between transmit and receive antenna? So maximum signal level by itself is not very useful, but if we can convert that number to gain, that would be very useful for us. Now, to do that, we're gonna do another measurement. And if you remember, we had this small horn antenna, and we calculated the gain of this small horn antenna in a different lab. So we know the gain of this small horn antenna at the frequency of operation, which is 10.52 gigahertz. So we keep the same distance as our measurements. So it was 1.6 meter in these measurements that we have. So now based on this measurement, which is consistent with our patch array measurements, we're going to calculate the maximum, we're going to measure the maximum signal level of this small horn antenna. And then we know what is the gain of this horn antenna and what is its MSL. So there is a relation between gain and MSL that we established. And then we look at the MSL of our antennas, and then we can calculate the gain of each of the antenna that we had. And that's essentially your responsibility to do that, to calculate the gain of series fed and parallel fed patch array. For measurement of the for this gain measurement, or to be more accurate, for this gain comparison measurement, I have mounted the smaller horn in its H plane. Currently it is vertically polarized, and I've also rotated the larger horn antenna compared to the previous measurement so that it is also vertically polarized. So now both of them are vertically polarized. I'm going to measure H plane, and then I'm going to use that to calculate the gain of the other two antennas. I don't really need to do an E plane of this antenna, so I'm just going to measure H plane of this smaller horn, and I use that. Now, one question that you might have is that we've already measured this in previous lab, so why you're measuring it again? The reason I'm measuring it again is that in each measurement, we may use a different distance, for example. Or we may have used a different cable. So we want to be consistent with these type of things. So that's why I'm measuring the H plane of a smaller horn antenna again. So I'm going to perform the measurements, and then I'm going to record its H plane. So to start the measurement, just gonna press start, and then we're gonna be measuring this. Something that I'd like to mention is that in the software we have currently 18 dB attenuation, so I'm keeping that 18 dB attenuation as it is. Of course, I shouldn't be here when it's performing measurement. I'm going to usually stand in the side, but I'm just talking. I'm gonna measure it again. That's just for demonstration, and then we gonna look at what's gonna be the result. So let's wait for this to be finished, and then we can come back and look at our data collection.
As we noted earlier, we need to measure the gain of the series fed and parallel fed patch arrays. So to this end, we're gonna perform a measurement with an antenna that we know its gain. When that's a small horn antenna that we know its gain at the frequency of operation 10.52. uh, so let's start the measurement. We have that a smaller horn antenna mounted in the H plane right now. The transmit and receive antennas are both vertically polarized. So after I'm done with this measurement, you're gonna see the maximum signal level of the small horn. Knowing that and knowing the gain of the smaller horn antenna from the previous measurements, then you would be able to calculate the gain of the series fed and parallel fed patch antenna. So because the E plane and H plane of the parallel patch was a little bit different compared to each other. We need to choose one of them to essentially perform our measurement. If you remember, the E plane and H plane of parallel fed patch were slightly different, about 1 dB different. So if you use H plane and E plane, you're gonna get about 1 dB difference in gain. So I'm gonna store this as the H plane, and similar to what we do always, I'm gonna set the maximum signal level to 0. So this becomes essentially my H plane of my uh, a smaller horn antenna. Now if I hide the E plane of the series fed, you can see different things here. This is essentially the H plane of the series fed. This is the H plane of the smaller horn. Now let's bring the H plane of the the other one, which is the parallel fed. So you see that as well. So this is the H plane of the parallel fed. So uh, you can look into the different levels of signals that we have. Minus 3.16 is the signal level, maximum signal level for parallel fed. Minus 5.67 is the maximum signal level for series fed, and minus 3.7 is the maximum signal level for the horn antenna. Now, based on these numbers and the gain of the smaller horn that we know, you should calculate the gain of the series fed and parallel fed patch antenna.